Section 4 from Unit 2 talks about changes in matters. These are going to be physical changes and chemical changes. The first type of change we're going to talk about is a physical change. This is a change that alters a substance without changing its composition. So this is like crumpling foil, cutting paper, breaking a crystal. Okay, you're not changing what it's made out of. That foil is still made out of aluminum. Okay, that paper is still paper, chemically speaking. That rock or crystal is still the same chemical. Okay, a type of physical change is a phase change is a type of physical change. Okay, so this is a transition of matter from one state to another. So this is like, if you think about it, this is from like solid to liquid, or liquid to gas, or solid to gas, or any of these things in reverse. Okay, you're going from one state of matter to another. Okay, you're not changing what it's made out of. Okay, think of it like ice melting into liquid water. It's still water. All right, it didn't change what it is chemically. Okay, so phase changes are considered physical changes. Phase changes occur because of changes in two things. The easy one is temperature. That's the obvious one, right? You get a block of ice out of the freezer and you leave it out, it's going to melt, right? Because it's warmer outside of the fridge than it is inside of the fridge. So the second option is pressure, and this is one that we don't usually think about. But if we go back to that, thinking about like, gas inside of a box here, okay? All right, it's moving around, all right? Well, what if we shrink the box, okay, and we increase the pressure of this gas? Well, now the box is, say, only this big, and I've got 4 particles in here, right? Okay, and let's say we shrink it again, and now it's just this big. Well, now my 4 particles can hardly fit, and at some point, those particles aren't separate anymore. They are actually held, they're together. Okay, and if you go back to what we talked about with solids and liquids, those particles are physically touching. That's a liquid. So you can actually liquefy gases by putting enough pressure on them. Okay, so temperature and pressure are the two things that can cause phase changes. The temperature that those phase changes occur at and the type of phase change that occurs help identify some substances. So for instance, here's a few of them. You can see water melts at 0 degrees Celsius and boils at 100 degrees Celsius. Ethanol, this is the alcohol that's in adult beverages. Okay, so that melts at negative 114 degrees Celsius and boils at 78.37 degrees Celsius. Aluminum, right? Aluminum metal melts at 660 degrees Celsius. Sodium chloride, this is table salt, 801 degrees Celsius is its melting point. Tungsten. Tungsten was actually, I know they don't really make them much anymore, but if you remember the old light bulbs with the filaments in the middle, that was made out of tungsten because it could actually, look at its melting point, 3,422 degrees Celsius. So that tungsten wouldn't melt. It would glow, but it wouldn't melt. Tungsten carbide is a compound. Mercury, okay, that's a liquid metal, melts at, negative 38.8 degrees Celsius and boils at 350 degrees Celsius or so. Lithium, carbon dioxide, right? If you know what carbon dioxide is, there is no liquid form of it at atmospheric pressure. This is dry ice, right? Okay, when it's cold, it's dry ice. It's the stuff that you exhale out of your body when you're done, processing oxygen. You're breathing out CO2. But as a solid form, right, we call that dry ice, and then it doesn't melt, it actually sublimes, so it's got a sublimation point of negative 78.5 degrees Celsius. So all these things here help us to identify these substances. If we weren't sure what something was, we could try to find its melting point or boiling point, which should narrow down, okay, what that substance is. And obviously there's a lot more substances than what's on here, but we can all this information is available online to us, readily, so we can go look it up if we test this in a lab. The second type of change we'll talk about is a chemical change. So this is a process that involves one or more substances changing into new substances. So it is now chemically different. It is no longer the same thing. New substances that form have different compositions, different properties from the substances present before the reaction. Okay, so it no longer behaves the same. It's got to have like a new boiling point or melting point, or it's got a different odor or a different color. It's chemically different now, right? It's no longer the same. It's got a new density, okay? So things about it that would normally identify it have changed, okay? The starting substances are called reactants, and the resulting substances are called products. We have reactants and products. So this is, we now have a term for what we're starting with. We're starting with reactants, we end with products. This example over here is a bunch of food that's beginning to spoil. Okay, this is not a physical change. All right, this isn't like cheese melting or something like that. That is mold growing on that, and all these things here, right? They're getting moldy. They're going to have new properties with them. They're not going to taste the same. They're going to smell different. Okay, this is a chemical change that happens to food over time. Okay, they're not the same, right? The sugar that was in these fruits, okay, or the lactose that was in this cheese, okay, that's going to be different. It's no longer going to be the same thing. It's changed, okay? It's a new type of chemical. Here are some pieces of evidence that a chemical reaction has occurred. This is not an exhaustive list, and it doesn't include every single thing as well that would indicate a reaction has happened, which we'll say down here at the bottom. So some things to look for. We form a new substance, right? That's fairly straightforward and obvious. We produce a gas. Now, we're not talking about boiling something because that would be a physical change, but you mix two things together and suddenly we get a gas forming, okay? It's just making sure we're clear on the difference there. It's not like we're just boiling something, but we mix two things together and suddenly there's a gas that's coming off of it. The temperature changes. You mix two things together, it gets hot or cold. This is how hot packs and cold packs work. Those instant hot packs and cold packs, same idea. A substance disappears. You mix two things together and one of them starts going away. A solid is formed. So you mix two things together and suddenly there's a solid. A color change occurs. It's not the same color it was before. A new smell is produced. Again, that's evidence that this is chemically different. And a good one is the melting point and boiling point of the substance has changed. Okay, that is a real indication that this is no longer the same substance. Here's an important point, though. There's not always visual evidence of a reaction, okay? So just because you don't see one of these things here does not mean that there was no reaction. Or we could still have a reaction occur without any of these things being seen. So when you're in lab, just assume that, if you're putting two things together, there's a chance it is reacting even if you do not see it. Okay, so I want you to take a look at this. It says to identify each of the following as a physical or chemical change. I'm going to label the first one up here number 1 and the second one number 2. And remember that if it's a physical change, okay, we're not changing what the substance is made out of. If it is a chemical change, we are changing the substance's composition. It is a new chemical. It is combined differently. Okay, so I want to see your thoughts on this, see if you can figure this out. With number 1 here, starting with this and going to this, and number 2, starting with this, going to this. So label it as either physical or chemical. So when we're talking about chemical changes, we often need to think about including the law of conservation of mass. Right? Remember that meant that in any process, matter is conserved. Matter is not created or destroyed in a reaction. Now, before what we had said was, we labeled this as the mass that you start with has to equal the mass that you end with, right? Those were the terms that we used to say this. Well, let's replace this with a little bit more correct terminology. What we're starting with, the things that we started with were called reactants. So let's call this now, instead of the mass that we start with, we'll just say the mass of the reactants needs to equal, and then what we end with are the products, so we'll say the mass of the products. So now we've got a little bit better terminology here with this. The mass of the reactants is equal to the mass of the products. All right. So this example up here in this picture, we got a test tube full of a chemical called mercury 2 oxide. Its formula is HGO. It's kind of this red colored compound. Real nasty stuff. Not something you'd want to be heating up regularly. This would need to be in a well-ventilated area. It'd be pretty bad to be breathing in this stuff, potential mercury fumes. But as you heat it up, it decomposes. It decomposes into mercury metal, which you can see here. Okay, mercury is one of the only liquid metal at room temperature, and oxygen gas. Well, as you heat this up, it looks like it would lose mass. If you were to go weigh this at the end, it would weigh less. And it's not because it lost mass, all right? That's because oxygen gas is escaping out of the test tube, okay? All right, oxygen is escaping out of the test tube because it's a gas, right? Unless there's a stopper on the end of this thing, the oxygen is escaping out, leaving just the mercury. Before, the oxygen was part of this compound in here. So if it ever looks like you've lost mass, it's probably because some of that compound turned into a gas and was lost. Okay, so we can calculate actually how much oxygen is let off. If we weigh this compound before we start, okay, we heat it up, and then we weigh the mercury afterwards. The difference between the mass that we started with and this mass right here is how much oxygen was lost. This is all just going back to the law of conservation of mass. Okay, so I'll read this problem and I want you to do it on your own. It's just kind of in words what was on that last picture. In an experiment, 10.00 grams of mercury 2 oxide is placed in an open flask and heated until it is converted to liquid mercury and oxygen gas. The liquid mercury has a mass of 9.26 grams. What is the mass of oxygen formed in the reaction? So go ahead and give this one a try.